Hey there, my name is Michael Wharton, and I'm VP of Engineering at KUNGFU.AI. Today I'm going to be talking about this brand new paper from FAIR at Meta. It's called Intuitive Physics Understanding Emerges from Self-Supervised Pre-Training on Natural Videos. That is an absolute mouthful, but what this paper is trying to get at is they've developed this new, or kind of extension of an old version they've been working on at Jan LeCun's lab, this new version of this pre-training objective that allows you to teach video understanding models rules about the physical world. Historically, that's been a really big challenge. AI models are just really, really not that great at it. We're good at learning underlying distributions. We're good at learning textures and shapes and all sorts of stuff. But when you play with a model like Sora or some of these other really popular video generation models, you can still detect these errors in things like physical consistency. Like, over time, you see someone moving across a frame and their face happens to just morph as they're going along, or it kind of doesn't pass the smell test for your human brain when you look at it. There's also a really canonical example of a ballerina, and you'll see as it twists, when it rotates, the ballerina kind of morphs and changes shapes, and they're just things that it's really easy for our brain to spot what's not going right, the errors. But for models, for whatever reason, the way we train them, or at least the current ways we train them, it's just very limiting and challenging. So the authors of this paper claim to have solved that, at least to some degree. And I think that, the reason Meta or their team's looking at this is probably worth talking about a little bit. They're also looking at robotics quite extensively. There's a memo that was released last week that was leaked, and it was all about establishing this internal research group that's focused on humanoid robots. And one of the big limitations in the robotics world is, data is just kind of hard to come by. You need a lot of training data to train, a lot of them are reinforcement learning systems. But to have a robot that could just operate in the natural world, understand the physics of it, interact with it, and do tasks that are actually useful for humanity, we're not there yet. And you can imagine if you have a model that really understands the physical world, it really understands how objects move, interact, kinematics, gravity, all that stuff that is really intuitive to you as a human being. We could generate arbitrary amounts of data and probably train some really impressive robots at the same time. So this paper is a step in that direction, and I think it's pretty noteworthy and worth talking through. There are a couple of model types that they talk about here in the introduction that I think or actually we're still in the abstract here. It's worth talking through here because these are pretty traditional approaches that this kind of builds on. So they're structured models, things where you encode your understanding into the model itself, things like kinematics. You can imagine a game engine. Some humans have to manually code up what the physics are that this game engine needs to be governed by. Even if it's something as simple as just throwing a ball, you need to make sure that the acceleration due to gravity is constant. You need to make sure that trajectory is following all those kinematic equations at every step of the way. And it's surprisingly hard to get a model to figure that out if it's trained end to end. These structured models are great, they work, but they're also very hard to create, and it's very labor intensive. That's there's a reason that tools like Unity exist to help you create some of these worlds. And then there are also these pixel-based approaches, which are the exact opposite, where it's just kind of the brute force method. You take a model or you take an input sequence and you try to predict the next frame, or you mask out regions and you try to do in-painting. You can have a model start to learn these distributions underlying, and it gets really good at that. But it's just a known limitation that these sorts of approaches just don't quite result in that natural understanding of the physical world that's requisite for a lot of these downstream applications. So let's talk about what they actually did. If you were to look for one takeaway for this whole paper that explains their approach, it's relatively simple. It's just this figure right here, figure 1B. And you can see they'll take these input videos, these input sequences. There's some depth to this stack. Those are sequential frames in a video. And then you can see these white grids drawn in here. That's just pixels, or rather groups of pixels. And then they'll intentionally corrupt it. And what they do is they jointly train an encoder and a prediction model. The encoder is this gray box here that you see duplicated across the figure. They'll embed the correct, the physically accurate sequence, and then they'll also embed the one that's been corrupted. And at the same time that they're training that, they'll train this prediction model that tries to correct for those corruptions in the latent space. That's a really important piece. And then figure out what that distance is between the corrupted and the uncorrupted one. And I think that's really interesting because you can imagine if you can train a model to understand what's wrong in this latent space, then it'd be really good at predicting, future steps, especially if the masking that you're doing is future frames relative to past ones. And it's no doubt inspired by this idea of predictive coding, which is a theory of cognition. This idea that human beings from your earliest years, when your brain's starting to form, you start to do this thing called predictive coding, where whenever you try to constantly predict the future, your brain sees errors in those predictions, and that turns into a signal that ultimately trains you to understand the physical world, be able to operate in it, etc. So that's sort of what this piece is doing. And at the same time, this encoder is trying to learn highly general abstractions that are predictable. And you can imagine that the type of abstractions that are predictable are physical principles that are relatively universal. They're very general, and they're things that govern the natural world that we have all these videos of. At least that's the theory of why this works. They tested it against a few different benchmarks, and I think it's worth dwelling a little bit on how they evaluated this model, because there's a little bit of funkiness going on here that I'm at least curious to know more about. That said, I don't want to diminish what the authors have done here, because I think it's very impressive research. What they've essentially done is they've taken each of these benchmarks and they've created these pairwise comparisons that are used as a source of evaluation here. In each of those pairs, there's one movie or short video clip that shows some physically plausible scenario. And there's actually a screenshot in here in figure 1C of one of those where, maybe you see some object that's rotating, maybe something that's translating. There might be occlusions present. There's all sorts of things that might be present. But the point is that it's a physically plausible scenario. And they contrast that against other sequences that are not plausible at all, that violate the laws of physics. And theoretically, if you have a video understanding model that knows about the laws of physics, the task of ranking those two videos would be trivial, be really easy. And they show that that's exactly the case. For this int-phys data set, they were able to do that. And they were able to get 98% accuracy, which is kind of wild. On these other data sets, they might be a little harder on GRASP and this InfLevel lab. I'm not as familiar with these guys over here, but to be able to perform even better than chance, especially in this domain where teaching these models to understand physics is just a known very difficult problem, I think it's really impressive. That said, the only direct apples to apples comparison that I think they made was this video MAE v2 model. As I understand it, that model is trying to do essentially the same task, but it's happening in the pixel space. It's not happening in this latent space. So it does well for sure, but it doesn't quite understand the laws of physics, which is what this paper is trying to fix. Now, the comparisons to KUNGFU VL72B and Gemini 1.5 Pro, I think those are a little more shaky. That's a little more apples to oranges. And to be fair, they even call attention to that in the paper. But what they're essentially doing is taking both of these videos for these multimodal models, providing them as input, and prompting the model to tell which one of those is the physically plausible one. It's not exactly the same. You can make some arguments that it's at least a signal in the direction of evaluation that we're trying to get at here. But despite that, being able to hit this kind of score on a benchmark that is at least trying to test against the very basic understanding of physics. I think it's a very impressive result, and I think it's it's a great step toward this sort of broader vision of being able to accurately model the world. A couple other things worth mentioning. So I think I mentioned this earlier, but this approach is called Joint Embedding Predictive Architectures, or JEPAs. This is a line of research that was started by Jan LeCun back in 2022, it looks like. And it makes total sense that this is inspired by how the brain works, that, the neuroscience field has had this sort of, thought in their mind for quite some time. It was only a matter of time before we extended this to the ML world. So it's no wonder that it at least works. This is probably a good keyword to know about here too, violation of expectation. This is sort of the way that they evaluate this model. In this, whoops, I had something else come up I didn't mean to. There we go. What they're using is this future predictive error as sort of a proxy for surprise. And you can imagine that when you predict, like here, it's showing next frame prediction. You can, in the input space, you can have a sequence of input frames. You mask out the future ones, and then you measure if this model's trying to predict or fill in the gaps there. What's the error with the truth that we actually know, the ground truth? You can imagine that a model that understands the physical world would have a really low prediction error, and a model that has no idea what's going on would have a high prediction error, which would be a violation of expectation. So that's what this term here is referring to. I think if we stick on the figures, that would probably make the most sense, just because it's visually interesting and easy to remember. I think this figure 2b is probably worth calling out as well. So there are various flavors of physical coherence or physical understanding for these models, and those are things that are tested for in different ways against each three of these evaluation data sets. Object permanence is the only one, I believe, that's tested against for all three. But if you look at these plots down here, essentially what they're saying is, it's a false dichotomy to say that models either understand the physical world or they don't, because humans operate on a little bit of a gradient as well. And they show that the errors, at least among these categories, from human cognition to these models, there's actually a correlation. We're not perfect. There are certain things that can happen in the physical world that surprise us that are still totally plausible. So they're at least trying to make the point that, yes, the model's not going to have a perfect understanding of the physical world, but at the same time, neither do humans, and those errors tend to be a little correlated. So I think it's an interesting note to at least dwell on a little bit. And this figure here, figure 3, it's a little more detail on, so they ablated the type of masking that's performed in this input sequence that we mentioned earlier. I think that's interesting, but this plot here is just sort of the picture's worth 1,000 words kind of screenshot. Oops. This is just showing that these are the various tests that they did and various performance across each of these. And, they vary a little bit here and there, but it looks like, at least on this figure, that the block masking approach seems to outperform the other two in at least these three categories. But yeah, take a look, see what you think, reach out to us if you want to discuss anything. I think this paper is great, and these world model type concerns are something that I know that our chief or our distinguished engineer here, ZZ Sai, he's following this stuff too. There's a lot of really interesting work to track. It's impossible to stay up to date. Just about, it's almost a full-time job just doing that. But yeah, if you got any thoughts or you want to talk through it, please feel to reach out anytime. And thanks for watching. Cheers.